Hi and welcome to John's Maths book. In this video, we're going to be looking at finding the area of a cardioid. If you like the video, then please hit the like button, and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. Let's look at how we find the area of a polar region shaped like a cardioid. To do this, I've sketched the polar graph of r equals 2 minus 2 cos theta. We know that the area across a polar region is given by the double integral across the region of infinitesimally small slices of area dA. This translates to the region being defined by an inner integral which integrates in the r direction between two values of r, and an outer integral which defines the region as we rotate about theta between two values of theta. The infinitesimally small pieces of area are defined by r dr dθ. So for the inner integral, we can see that it begins at the origin where r is equal to 0 and extends out to the polar curve, so where r is equal to 2 minus 2 cos theta. To find the limits of theta, let's look at how the polar region is plotted using a graphing tool. The graph of the cardioid begins at the origin, so when r is equal to 0 and when theta is equal to 0. When theta equals 90 degrees or pi by 2 radians, we see that r is extended to 2 from the origin. When theta equals 180 degrees or pi radians, r is now 4 from the origin. And when theta equals 270 degrees or 3 pi by 4, r is once again a distance of 2 from the origin. And finally, when theta is equal to 360 degrees or 2 pi, r is back at the origin and the cardioid is complete. Now let's look at how these limits can be manually determined with the help of a graph of the cosine function and our polar curve r is equal to 2 minus 2 cos theta. We saw that the cardioid graph began when r was 0. So let's plug 0 in for r into our polar equation. This leaves 0 is equal to 2 minus 2 cos theta. So for this equation to be satisfied, the cosine of theta when multiplied by minus 2 should be equal to minus 2. Therefore, the cosine of theta must be equal to 1. As we can see from our cosine graph, the first instance where cosine of theta is equal to 1 is where theta equals 0, and the equation is satisfied. Theta equals 0, therefore becomes the lower limit of our outer integral. We know that the cardioid is complete at r equals 0, so we have the same equation when we plug 0 in for r. So 0 equals 2 minus 2 cos theta. Again, the cosine of theta must equal 1 for this equation to be satisfied, and using the graph of cosine, we see that the second instance where this is the case is where theta is equal to 360 degrees or 2 pi radians. When we plug 2 pi into our equation for theta, we see that our equation is now satisfied. So theta equals 2 pi becomes our upper limit of integration for the outer integral. Let's now evaluate the double integral. So beginning with the inner integral, we want to integrate from r equals 0 to r equals 2 minus 2 cos theta, r dr. And the antiderivative of r with respect to r is r squared over 2. And we need to evaluate that between 0 and 2 minus 2 cos theta. If we plug in 2 minus 2 cos theta for r, we get 2 minus 2 cos theta all squared divided by 2, and minus the lower limit of 0 gives minus 0. If we expand this bracket and divide by 2, we're left with 2 minus 4 cos theta plus 2 cos squared theta. Moving on to the outer integral, we need to integrate from theta equals 0 to theta equals 2 pi, 2 minus 4 cos theta plus 2 cos squared theta d theta. Evaluating this term by term and beginning with 2, the antiderivative of 2 with respect to theta is 2 theta, and we need to evaluate this between 0 and 2 pi. The antiderivative of minus 4 cos theta with respect to theta is minus 4 sine theta, and again we need to evaluate this between 0 and 2 pi. To integrate cos squared theta d theta, we can use the double angled trig identity where cos squared theta is equal to 1 plus cos 2 theta divided by 2. If we multiply through by 2, we have 2 cos squared theta is equal to 1 plus cos 2 theta. Integrating 1 with respect to theta, we get theta, which we need to evaluate between 0 and 2 pi. And integrating cos 2 theta with respect to theta, we get 1/2 multiplied by the sine of 2 theta, which we need to integrate between 0 and 2 pi. Plugging in the limits of integration for each of these terms, and beginning with 2 theta, we have 4 pi minus 0, and for minus 4 sine theta, we have minus 4 times sine 2 pi minus 4 times the sine of 0. And then for theta, we have plus 2 pi minus 0. And for 1/2 times sine 2 theta, we have plus 1/2 times sine 4 pi minus 1/2 multiplied by sine of 0. All terms involving sine evaluate to 0 and therefore cancel out. We're then left with 4 pi plus 2 pi, which is equal to 6 pi, and our final answer.